Well, hey folks, Mr. B back again. We're going to take this atomic theory and push it a little further. Last time we met, we were talking about Dalton's model of the atom, where atoms are these indivisible, unbreakable, almost like pool ball, billiard ball elements. Thomson with his plum pudding model, where everything's just kind of dispersed. And then Rutherford, who went with a planetary model, where electrons are going around the nucleus. Okay, so where does this go? Well, it's time to enter Niels Bohr. Now, what Niels Bohr came up with the idea was that electrons occupied specific orbitals around the nucleus, and that they essentially had different energy levels. Now, when you look at this diagram, there's one thing I do want to point out, right? And the most important thing is that these electrons, there's one here, there's 2, 3, 4, 5, 6, and 7. Okay, so if I haven't missed an electron, you need to know that when it comes to the number of electrons is equal to the number of protons. Okay, so if this has 7 electrons, then you know that this thing has 7 protons. And that is the atomic number. Excellent. So when we're talking about atoms, electrons and protons balance out. Atoms are neutral. So we can think of it this way. 7 protons is like plus 7, and 7 electrons is like minus 7. Just put a line to divide this. So what does that mean? That means that there is no charge, because the positivity is balanced out by the negativity. Okay, so Niels Bohr, he takes the Rutherford model further and talks about what's going on with the electrons. And there's a huge amount of material. Here, he won a Nobel Prize for this in 1922. Folks, Niels Bohr worked with the greats. He worked with the J.J. Thomsons, and he worked with the Albert Einsteins. But more about that later. The Bohr model envisions these orbitals, right? And you could see them. They're these shells here, like this. And the idea of the shell was that electrons would occupy certain orbits, and when they filled those, they would then occupy the next orbit. Now, if we're taking a look here at sodium, okay, sodium has 11 protons, which means it has 11 electrons. That is for the element sodium. Okay, we'll talk about these things called ions later. So, equal number. If you think of them as little moons, I guess, going around, or satellites going around in orbit, you see that there's 2 on the inside, right? And in the next orbital, there are 8 in total. And that orbital appears to be full, so, missed one. When that orbital fills, then the next orbital begins to fill, moving out, and we've got 1 electron in this outside orbital. 8 plus 2 plus 1, 11 electrons. And it follows that rule, right? Where 11 electrons and 11 protons are balanced. Now, Niels Bohr idea, the idea that you've probably worked with this before in Science 9, you show the electrons in each of the orbitals. And that's the thing about Bohr diagrams. It can be a lot of work because you're showing all those electrons. Now, what we'll move into in Chemistry 10 is we'll look at valence electrons, which is the electrons only in the outermost shell. Okay, but it's important to understand the Bohr diagrams before you do the valence electron model, sort of that comes next. So, what element is this? Let's do a little scribbling. This element, let's keep track of the electrons. Specifically, there's 2 here. Okay, so this orbital holds 2. And there are 8. And you notice how they put them in pairs, right? So we've got 8 there. And then the next orbital, 2, 3, 4, 5, 6, 7, 8. This orbital has 8. Okay, so when we take a look at something like that, we say, well, if the number of electrons is equal to 2 plus 8 plus 8, folks, we have 18 electrons. If it's 18 electrons, then the protons have to be the same number. So let's take this a little further. What's the 18th thing in the periodic table? Well, I've got this waiting for you here. If we look at the atomic number, we've got hydrogen at 1, helium at 2, lithium 3, beryllium 4. And if we go across and we find the 18th item in the periodic table, that's argon. And that's one of those really, really, really stable things that we call a noble gas. This chemical family is these are the kind of gases, for example, like neon, when you run electricity through it, it puts off these wonderful colors. Neon, argon, there's argon lasers, but more for that in another time. We're looking at element number 18, argon. Neat thing in this interactive periodic table, if you click up here, there's some advanced stuff, but what I really wanted to focus in were you can see the green spheres, right? And we're looking at electron configuration. You can see 2, 8, 8. Now, anything that has 8 electrons in its outer shell is pretty satisfied, and we say that's the octet rule. Octet is basically what we're saying is it is an 8 electron filled shell. So there's 8. If you've got a full octet, you're happy and you're really stable. All right. So we have deduced that our friend right here is argon. Just wanted to come up. There we go. Now, there's something kind of subtle there. Do you notice that it had 3 full shells? The first shell holding 2, right there. Second shell holding 8. And the third shell, oh, I forgot one there, holding 8. It has 3 shells. So you can think of it as having 1, 2, 3 orbits where the electrons can fill, right? There's the first, there's the second, there's the third. Now, if you pay attention to that, you're saying, wait a minute, it has 3 shells, and it's mentioning here, it has 3 electron shells, so it's in period 3. What do we mean by period 3? Go back to our interactive periodic table here. If you look, hydrogen is in a row. So there's hydrogen, there's helium. Those rows in the periodic table are periods. Lithium is in the second row, or the second period. And our friend argon here is in the third row. Now, each of these rows is important because you'll notice that there is the first row has this, the second row, I guess I'll just write it like this here, and the third row here. So what we're talking about is every time you look at a row, it gets one of these shells. 1, 2, and 3. Now it turns out that argon filled each of its orbitals. The first orbital can hold 2 electrons, the second can hold 8, and the third can hold 18. And at this point, we'll consider that outer shell full. Now there's a little bit more to this, but what we give you kind of in the early going is the 288 rule, and then we can expand on that later. It's a simple rule that says the first shell can hold 2 electrons, the second can hold 8, and the third holds 8. In this case, argon is a noble gas because it's obeying the octet rule. It has 8 electrons in its outer shell. So there becomes this pattern, this arrangement pattern, and here it's a little bit easier for you to see. Here's your first row, and you notice that there's only 2 elements in that row. That's a little bit of a hint there. The reason why it only holds 2 electrons. There's only 2 things in that row. If you go to the second row and you go to the third row, what you'll notice is Second row has 2, 3, 4, 5, 6, 7, 8 items. Third row as well. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so you can see what happens in the case of, we'll look at lithium, for example. Lithium is atomic number 3. So it has 3 electrons. And essentially what lithium did is it filled its inner shell, and once that shell was full, the next orbital starts to fill, and that's where that last electron went. And this shell fills, and you'll see, I'm just going to pencil them in, right? Fills in its extra electrons to the point where, oops, focus on this. It fills them as we go across until that outer shell is completely full and we're at a noble gas. In this case, here's the 8 electrons. Neon is obeying the octet rule. It's an example of it with a full 8 in its outer shell. Now, neon with just one more electron turns out to be sodium down here. Okay, so what we're doing is we're drawing things called Bohr diagrams. I'm going to recreate one of these Bohr diagrams, looking at atomic number, and just going to go to the periodic table here, this interactive periodic table, and let's say we have chlorine. Okay, atomic number 17. Okay, got it. So what's the Bohr model for something like a chlorine, right? Now, chlorine, atomic number 17, leads us to know that we have 17 protons, and so we have got 17 electrons. Now, we'll keep this kind of simple. We'll just draw the nucleus basically like this, right? And we'll say what we're looking at is 17 protons. Okay. Now, we'll just switch the color up so it's a little bit more, just a little easier to follow. I'll use an opposing color, red. And in our first electron shell, which I'll just draw sort of as a dashed line, I've got 17 electrons that I have to disperse. So I'm going to follow that 288 rule. And I need you to understand that 288 rule, really we don't go past calcium with that rule. And the reason why, without getting technical, is there's a lot more to these orbitals than you realize. They're not just rings. They actually have wonderful three-dimensional shapes. Electrons are found whizzing all over the place, and they start to produce these patterns. But that is for more advanced chemistry when you study SPDF orbital theory, and it all makes sense. At least it did for me once I finally got there. All right, so let's pick, I don't know, let's pick an interesting color to go with red. Let's choose something, let's pick green, opposing color. Okay, so atomic number 17. I'm going to fill in 2 electrons. So we're going to go with that 2-8-8 rule. So 17, I've put in the first 2, so I've got 15 to go. So this is full. 1, 2, 3, 4, 5, 6, 7, and 8. So by filling this up, I've now gone from, I have to get 17, so I've got 2, then I did 8, so I'm at 10, right? So this is done, and how many to go? Well, I've done 10, I got 7 to go. Okay, so just kind of go like that to help you. 15 at that point, 7 to go now. Okay, so I will say 1, and what you do is you almost, you put them like this to begin with. You draw 4 individual ones like that, and then you pair them up later. So I had 7 to go, so I've got 4, 3 more. 1, 2, and 3. And you'll notice this poor little guy down here doesn't have a partner. Well, that's because I've put in all of them. 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'll just jump over here for a sec. 15, 16, and then there's your 17th electron. So all of our electrons are accounted for. So what did I do? Well, I realized that the atomic number was 17, and I had to put in 17 electrons. Okay, not bad. Head back to our show here for a second. There we go. The thing about these noble gases is you notice that their shells are always full. Helium is a noble gas, and its internal shell, which only holds 2, is full. Helium is a little bit different because it can only hold 2. We don't call that an octet, we call that a duet. Right? But these guys down here, argon, for example, its outer shell is full. So are its inner shells. But we're just kind of looking at the outer shell in this example, saying it's obeying the octet rule. So draw the, what's it asking us here? Oh, draw the diagram for a nitrogen atom. Okay, we can do that one too. If you look at nitrogen, atomic number 7, and that's not too difficult a one. So atomic number 7. So the protons equal 7. So I know that I've got how many? 7 electrons. I don't want to forget that 2, 8, 8 rule. So let's draw a nucleus, 7 protons, right? And we won't worry about the neutrons for now. We'll just discount them for this. And let's get some shells in there. Ooh, not the best circles. Okay, so we're looking at 7 electrons. So to begin with, we've got 1, 2. Okay, so that fills the inner orbital. And that means I have, well, I've got 2. I've got to get to 7. I got 5 to go. 1, 2, 3, 4, 5. Okay, not bad. So when you're all said and done, double check your electrons, make sure you didn't miss any, right? And there's, that looks good. Okay, so we've got our 7 electrons. We had filled up our first shell with 2, and then we had gone out to the next shell, and this is just a little bit of shorthand here. I'm just drawing the edge of the shell, and there were 5 electrons that I needed to include in there. But the way you draw them, in your first shell, right? In your first shell, you put your electrons opposing like this, and then in the second shell, you draw them in like that, and then start making pairs until you fill the shell. Okay? So here we go. This graphic here, this is okay, but this is the more traditional way to show a Bohr diagram. Okay, so I just have to, oops. I'm going to go back to go away from full screen here, because I need to see other aspects of my slideshow. There's some chemical formula work here I will get back to. We'll come back to at a separate time. But in this case, when we look at Bohr diagrams, what is going to be coming up is when we talk about what the atoms are going to do when they decide to make relationships with other atoms. And you've probably seen these before, so I'm just mentioning, but I'm not going to get into it today because I was only going to do Bohr models. We're going to look at something called ionic and covalent bonds. Ionic bonds, when metals and nonmetals exchange electrons and accept electrons, right? And covalent bonds, which is a game of sharing. And that is going to be pretty important. I'll bring back the Bohr diagrams in that case to show you how that works. But for today, we just wanted to keep it sort of short and sweet with Bohr diagrams. And for fun, let's go back and just see if we can do one more. See if we've got this figured out. Picking something off the periodic table. You really do not want to go past calcium. Okay, calcium is atomic number 20, 20 protons. There's more to knowing the electron configurations than Bohr was able to describe with sort of simple modeling. And if I click on calcium, for example, up here, you'll see where it says electron configuration, and it says something in brackets argon, and then it says 4s2. That's the additional theory that you'll get in, well, senior chemistry. We'll just put it that way. But if I was to do a Bohr diagram for something kind of up to about, let's say not too hard of a one. Let's pick aluminum, atomic number 13. Okay, let's make sure we know this. If aluminum is atomic number 13, what was I using here? Blue and red and green. Okay. All right. Forgot which one I was going to do. Aluminum. It's good old number 13. And that tells me a lot right there. 13 protons, 13 electrons. Okay. So I'll put 13 protons in the middle, and what the heck, I'll just draw solid orbitals this time. Just that my circles are really lousy with an Apple pencil, but that wasn't so bad. Okay, so if I've got 13, I have to follow that 2-8-8 rule. So 13 minus 2, you want to think of it that way. That's another way you could do it. 13 minus 2, I have 11 more to go. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So if you take stock of how many we got, we took 13, we had 2, right? So there was, at this point, 11 to go. I drew in 8. So I have to go to my outer shell. That means I have 3 to go. So I kind of do this sort of north, south, west, and east. I put the electrons really at this location, and then I go like that, and then I go like that. And if there were another electron, I would put it over there before I make pairs. That's a good way to draw these. Okay, so I've assigned my 3. And what you'll notice is that the third orbital, which could hold 8, is only holding 3. Well, that's because aluminum, its atomic number is 13. So it filled this up with 2. This took us to 10. Right? And then we had just 3 remaining. Okay, so you can see that aluminum has these 3 electrons in this outer sort of orbital, and this is our Bohr diagram for aluminum. The more Bohr diagrams you get, that you do, the better you get at this. But rest assured that we won't be doing Bohr diagrams forever. You did a lot of them in grade 9. We're going to focus essentially on the outside, this very last orbital here, when we're working with valence electrons. So aluminum, at this point, has 3 electrons in its outer shell. Okay, so ladies and gentlemen, that's it. Kind of short, sweet, just a quick review of Bohr diagrams. At least I hope it was quick. Ciao.